Okay, interpreting a drawing that uses GD&T is a matter of looking at the implied symbology and the notes and reaching the one and only one correct understanding. Okay, that's how we go about making parts that for interchangeable assemblies that can fit. We need to dimension the thing properly using the proper standards and such that when somebody else looks at the drawing, say, we make our part drawings in Akron, and then we send the parts somewhere else to get manufactured. Um, the only way to do that would be by having proper interpretation on both sides. Us putting the GD&T symbols on the drawing, and the supplier improperly interpreting those. Okay, so again, it's very important. Um, and then we have to request corrections or ignore them if errors are discovered. I mean, that just causes problems. Interpreting only an ability to understand meaning when dimensions and tolerance completed in compliance with applicable standards. Okay, so there's no guessing here. You work to the standards and everything is understandable, and you have one interpretation and you have no ambiguity. Um, Here are the skills required for dimensioning. GDT interpretation is a matter of looking at the symbols. Request corrections. Okay, I think I've seen this one before. Okay, discussion of principles. So you need to be able to discuss with others. And if you could sit down with others in your design team and talk about knowledge of principles, methods, and specific terminology, you can get to that proper design. Um, and you need to consider various levels of capability and understanding, because there's a lot of newer people that work with you. There would be the older guys who know more about things. So you need to work with people's understanding and explain what you've done and why. Okay, I do that all the time as a design engineer. I go talk to the manufacturing engineer, I go talk to the quality engineer, and here's why I put this dimension on the drawing. Here's how I came to it. And I say, oh, that's a good approach, etc., etc. So that's how we get to our proper understandings. Now, all dimensions have to be properly calculated to allow the maximum amount of part variation while still ensuring the proper function. Okay, so you want to be able to give a lot of tolerance only when you can, um, because you don't want to jeopardize the quality of the function at the top level assembly. You can't have it too sloppy. So design engineering is kind of like an art. How to give them the most tolerances, how to give the manufacturing the most tolerances possible, and still come up with a design that meets all of your needs. And you cannot assume tolerances. They have to be calculated. Technical terminology. So you need to use exacting terminology, because that prevents one term with multiple definitions established. No, no. And then colloquial terms used in industry can lead to confusion. Like some plants use one term for something and other plants would use a different term for it. So we need to try to avoid that. That's why we use standards. Let's talk a little bit about the product definition data set. Um, that is the entire collection of documentation that's used to provide descriptions of requirements for a product. So that could be either in an annotated model, and typically we work in aerospace, we work with multi-view drawings, notes, lists, and a list of required materials. That's what we usually work to. Um, Now, let's talk a little bit about a model. So a lot in your textbook they talk about applying GD&T to models. So this is kind of what it would look like. You would have a solid model on your screen, you would have an annotation plane, and then you could put this stuff on there. We're not really going to be working with models, but I just wanted to show you how it's done. But yeah, so I think most of our focus in this class is on the orthographic views, not on the solid models. Dimensions and noted requirements that may or not be visible but available by interrogation of the model. So you can find these things by looking at the model. So let's take another peek at this one here. So here is how we can show dimensions on a solid model. hole sizes and stuff like that. So we can annotate on the solid model. And your book tells you all throughout the textbook how to do that on a model. Um, and it's good to see that, but it's not something that we're physically going to be doing in this class. We'll probably work more with orthographic views. A dimension, okay, so you have an extension line, you have a dimension line, and then a dimension value. So that's how dimensions are shown. Um, Next one, nominal values. Nominal size is the size, value, or condition feature by which the feature is known. It's not required to be the same as the dimension value. It may be either a dimension limit, or it may not lie within the limits. Nominal just is a general size designation for it. Um, Orthographic projections. This is what you've done in the first two classes in your drawing classes, and also in the working drawings class too. It's a process used to manually create multiple orthographic views to define mechanical parts. It's mostly completed by CAD software if created from a model, and that's really helpful because you can arrange the views better. You can cut sections really easy in using CAD that you couldn't do if you were just doing this on the board. And understanding how to read the views is a very important skill, and I think you guys have been working on that um, all along in your college career. So let's talk about angles of projection, because this is a pretty important point, because there are two projection systems to establish the known relationships. I'm talking about creating those orthographic views on a mechanical drawing. There's first angle projection and there's third angle projection. And really, it's just how the views are arranged. And I'll have an example of this on one of the next slides, but you gotta know which projection is being used. I think in America we typically would use the third angle projection. I know over in Europe they use the first angle projection. So I've seen both types of drawings, and it can be really confusing if you don't know the difference between the two. So the views appear as though part features are projected on a flat surface. That's what we do with orthographic projection. Okay, and the next slide tells you the difference between third angle projection and first angle projection. Okay, and the easiest way for me to explain it is, on your orthographic projections you have a front view. This is third angle. This is what you're typically used to. And then what you would see here in the right side view is actually looking at this face, as if you rotated the part and you were looking at this face right here. Okay, the right side view is placed to the right of the part, and then the left side view is looking at this face right here. And then here's the front view again, and then the bottom view is actually as if you're looking up at the part from the bottom, and the top view is actually looking down. Okay, well, first angle projections actually backwards how it's done, and so like the right side view is shown on the left side of the part, and the left side view is shown on the right side of the part. So this right side view is actually looking at the part from this side here. Okay, first angle versus third angle projections. Now you'll always have this designated on the drawing. Let me show you a drawing I brought in from work. Yeah, so right here, so this is the title block on one of our drawings. You'll see unless otherwise specified, dimensions are in inches. We talked about that earlier, so I know that all these dimensions here are in units of inch. And then we have a block tolerance designation here. We have the material, and then here is our third angle projection key. Okay, so that says, well, this view here and this view here are related to each other. In this view here, I'm looking at this face of the part, and then in which case I see two concentric circles. So that's how we designate third angle projection. So again, is very important. You should know the difference between first and third angle projection, and look for it on a drawing. I mean, because if you didn't understand that you were looking at a drawing that was created in first angle projection, you can make a serious error in manufacturing parts. Now here's the third angle projection symbol. So it looks just like what I was telling you about. Okay, so I'm looking at this face, so I see two concentric circles, and then this one, it's done the other way, where I'm looking at this face, and the two concentric circles are on the other side of the part. Okay, so again, very important. Projection lines, you learned this in your first drawing class. They're generally used to relate the adjacent views. And then future trends, we're going to be doing CADs, we're going to do solid models, CNC machines, computer-aided manufacturing, and then paperless factory to eliminate hard copies, and then finally additive manufacturing. These are all the ways that we're going in the industry. Okay, so this is the last movie for Chapter 1. Thank you.